figured
I
it
can
out.
only
So the
look
meter
for
was
my
nice,
all
so
period,
yeah,
right?
okay.
So I don't want to like overload myself with.
Nice haircut.
Thanks.
For like the topology stuff in the analysis.
See, that's the thing. I didn't
I guess you
really enjoy it that much. I fucking hated topology. But I feel like it would be better if I
Welcome to the topology seminar, bro.
It's gonna have a lot of fun here, yeah.
Yeah, I don't think this is the seminar, guys.
So maybe if I take the topology course, I'll be more interested in it.
Oh yeah, it's way better than the metric topology.
I don't-
351.
I think Blake from what I saw them doing, he did a pretty good job of giving you a feel of what it's gonna be like.
Yeah.
Actual topology is way better than the metric stuff in real analysis.
Yeah, but you have to know all that stuff.
I mean, it's more general. Like I first learned like the actual topology.
Yeah, it's kind of more like playing fun little games. It's like, oh, you have a compact set and a closed subset, show it's also compact. But don't talk about metrics.
Yeah, that's the thing. I like metrics. So like
Oh.
the topology was just like,
Franny was doing it, I have no idea.
Oh, he knows, yeah.
I think I knew
Which
that.
one? Was it this one or this one?
The black one.
The black one?
So at least the way you want to do it is, first, whenever you put it, you have to always point to the camera, fortunately.
Are you kidding me?
Yeah. And it goes in pairs, so usually, at least the way I use it is with setups, so the number 1 is the first 2, number 2 the second 2, 3 the other one, or the other one. So I would just go like 2, which is the should point better.
Mind you, he did this for an entire course.
Yeah.
He recorded.
So I usually go 2, which is gonna be those 2. Then I use the arrows to go like middle 2. So 2, 3, and 4. Then I will go for number 2, which goes 4 and 5. Oh, sorry. That's 2. Go for 3 and 4. Then you go for number 3, which is gonna be the next 2. Or you can just use the arrows if it's easier.
Okay, cool. Alright, so I just have to point towards there now.
Yeah, that's the main part.
Cool. Oh yeah, okay, that works. Okay, I'm good whenever I'm recording. And
Okay, so we're good to go?
yes.
Okay, welcome back to the topology seminar. We had a brief sojourn where we talked about differential stuff, but we're back to some pure topology again. So this is following up the 2 talks I gave about bundle theory and vector bundles. So if you were there, that's good, and if you missed it, then hopefully you'll understand something. So I'm going to motivate why are we talking about K-theory before I even talk about what a definition should be. So if we just consider our old space X, pick any space X, pick F a field so we can talk about vector spaces over F, and consider all of our vector bundles modulo isomorphism. Just take isomorphism classes. So we can always add together vector bundles, and there's a unit for this given by the 0 bundle. And this structure forms a commutative monoid, but one problem is that there's obviously no difference. There's no negatives for bundles because over every connected component, the bundle is going to have a non-negative dimension. So you can't add a bundle to reduce the dimension. So you're not going to get additive inverses here. If you throw in the tensor product, this also distributes over sums, and this is not quite a ring. It's something called a semi-ring. It would be nicer if it was a ring. So the issue being that commutative monoids, there's not really great structure theorems for that, but like every undergrad in group theory sees fundamental theorem for finitely generated abelian groups. So we'd really prefer to have a group instead. So the idea is that there's going to be a way to analogously, similar to the way that we go from the natural numbers to the integers, we can take our commutative monoid Vx and groupify it to result in the thing that we're going to call K-theory of X. All right, so the plan is that we're going to talk about this groupification procedure. There's a formal algebraic groupification introduced by Grothendieck, and there's a more geometric thing called stable equivalence, which results in a different thing, and this is a kappa. This is how I draw my kappas. They look a lot like a K, but it's different. And for a nice enough class of space, it's going to turn out that these are the same thing. So it just gives us 2 ways of viewing the same object. We're going to look at some easy examples. All we can really do for now with our hands is think about spheres. Using some local trivializations, like we talked about earlier in the seminar, we can really easily figure out how to describe vector bundles over spheres and try to take that description and turn it into a calculation of this group K. Then we get to much more advanced stuff, and I'm not going to be able to prove like anything in this talk. But what we're trying to get to that makes K-theory sort of workable is this thing called Bott periodicity. I'll explain more about what that is when we get there. But in order to talk about it, we'll have to consider relative K-theory. We have to consider things like external products, right? You can have internal sums and tensor products where you're over the same space. But if you have two different spaces, you can also have an exterior product of bundles on that space, and that's going to give us a product structure on the K groups of these spaces. And time permitting, we probably won't have time today. I might have to leave this until another time as well. We'll talk about the fact that K is a generalized cohomology theory. So Francisco, in his talk about cohomology, he gave us a grocery list of what we'd like our cohomology theories to satisfy. One of them was that it should be, for a point, when you evaluate it at a point, it should be concentrated in degree 0. In K cohomology, that's not the case. But periodicity is going to tell us actually that this thing is Z in every even degree and 0 in every odd degree. So it's absolutely not concentrated in degree 0. It's unbounded in both directions. And it's actually, the interesting thing is that it's periodic. It's a two-periodic theory. So that's the plan so far. If there's questions or comments yet, that would be cool, but I don't expect it has anything. Okay. Let's just start.
Oh, I have a question.
Sure.
Can you explain like what you mean by tensor product is an isomorphic iso-ring operation?
So just that once we turn our Vx into a group, we want this semi-ring to become like a ring.
Oh.
So we don't want to do it in a way that breaks the tensor products distributing over the sum.
I see.
Yeah, we'd like it to become a ring. Yeah, I'm not going to emphasize that too much just because of time. Right, so let's talk about groupification. So we'll talk about a commutative monoid. This is just an abelian group without additive inverses. And we can consider so we can define a relation on, I guess I should motivate this first. So one way to think about the integers as being constructed out of the natural numbers is to think about them as being formal differences of natural numbers. And this is one way that you see them constructed in a lot of contexts. You consider n to be the positive part and m to be the minus part, so this is standing for something like n minus m. And you mod out by the relation that two tuples should be related if they differ by a constant. So essentially you want n m to be related to n plus c, m plus c. So this isn't a symmetric relation, but you can just add in more relators to sort of generate an equivalence relation. So we do a similar thing here. Consider the relation on m cross m generated by same thing. So something representing a formal difference. If you change both of the entries by the same amount, it should still represent the same formal difference. And now we're going to define the Grothendieck group, not to be confused with the Grothendieck construction. It's something different. So this is in symbols, GRM is defined to be the product minus modulo this relation. So, and then fact, right? This is an abelian group. And that abelian group. The inverse of nm obviously is going to just be the pair m n. So that's something that we can do now that we have pairs. We can just switch them. So another important fact is that there is a universal morphism. I'll just call it gamma here. It goes from M, your monoid, to the Grothendieck construction. So in the case of N into Z, you just have the natural embedding of N into Z. And what you do is you just take your element to the pair thing minus nothing. So it's just a formal difference where you don't subtract anything. It's universal in the sense that for any monoid homomorphism, where G is a group, there should be a unique factorization so you have M, you have your homomorphism to G, you have your natural homomorphism to the Grothendieck group. And so I'm saying that there should be a canonical and unique phi bar coming from the Grothendieck group to G. So one way you can call this, some people call it this, is a group completion. It's like you're just adding just enough to make it a group. And this is captured by the universality of this morphism. So the fact that there's a unique extension means that this Grothendieck group is kind of like the smallest group that you can get out of your commutative monoid in a natural way. Okay, is this way too far away, or is this still a good board?
That, I think for audio, maybe, yeah, if that's okay.
Yeah, okay. And that second to last line, where G is a group, right? No, where is?
Yeah. G's group here. Yeah. So you have a monoid homomorphism to a group, then you get a canonical extension to the group completion. So we're going to just plug in our favorite commutative monoid now. So for X space, we're going to say Kx. This is the Grothendieck group of our monoid of complex vector bundles. So for the rest of the talk, we're going to be talking about complex vector bundles exclusively. The theory works out much better for them. In terms of defining things and all of that, everything is the same as it is for real vector bundles, but the things like Bott periodicity, computing the examples of spheres, you're going to get different values for real K-theory. So we're just going to focus on complex K-theory today. I'm just letting you know that real K-theory, there's a lot of other theory for real K-theory, and there's also a symplectic K-theory that people care about. So I'm going to write down, emphasize that we're talking about complex K-theory. And so I'm going to apply the universal thing over there as an example. So if X is connected, then we get a monoid homomorphism from vector bundles to the natural numbers just by spitting out their rank. We're specifically not going to assume that the rank is the same over every connected component. So in order to make this well defined, I have to assume that X is connected. So then we have N sitting inside Z. So now this monoid homomorphism becomes a monoid homomorphism to a group. And so here we have our thing down to K-theory. And so we actually get a well-defined rank function on K-theory, which now takes values in the integers instead of the natural numbers. So it's possible for elements of our K group to have negative rank in a way that absolutely makes sense, as long as we're only considering one connected component. And we're going to use this to do the first example. if we take K-theory of a point, which is the most connected space you can possibly have, and then we take its rank function to Z, this is an isomorphism. And the idea being that we already have an isomorphism between isomorphism classes of vector bundles over a point. Those are just vector spaces. Those are just exactly distinguished by their rank. We already have a rank isomorphism going to the natural numbers. And you have to kind of convince yourself that this is going to give us an actual isomorphism on the Grothendieck constructions as well. But I'm not going to go through the details. I don't have time, and I didn't take the time to think about it either.
Is it really that complicated? I feel like, because like this induced map should just be like the rank of the first pair minus the rank of the second pair.
Yeah.
Oh, the first component minus the, I feel it should be like obvious.
That it's an isomorphism? Yeah.
Yeah.
Yeah. So, exactly. So manifestly, when we think about this Grothendieck group, we call these things virtual bundles. So elements of this Grothendieck group just look like differences of bundles V minus W. And for K of a point, so let's, the rank of this virtual bundle on the Grothendieck construction is really just the difference between the ranks of the bundles. And so you can check it's definitely going to be surjective. It's easy to cook up surjectivity. And injectivity just means that whenever something goes to 0, these are going to have the same rank, which means that as bundles over the point, they're isomorphic. So it's actually giving you the 0 element of K-theory. So yeah, it's not that complicated. Okay, so it's a good start. There are more questions at this point because we're about to switch topics a tiny bit.
X is just an arbitrary topological space?
Yeah, in this case, I'm just taking any space X. You just have this monoid of vector bundles. You can form the Grothendieck.
Yeah.
I guess like X has to be nice enough that the isomorphism classes of vector bundles form a set.
Yeah, I was gonna ask about that, like, it's
But
a
it,
set, like.
it should be fine.
Yeah.
X is a set. So maybe, yeah. But for our cases, we're just going to be talking about compact Hausdorff eventually, so that's definitely good enough. Okay, so now I decided I was going to introduce reduced K-theory. So it's a common thing in algebraic topology. When you're talking about pointed spaces, suddenly all your cohomology theories get reduced. So we're going to say for x naught in X, define, this is the reduced K group. I'm just going to write a tilde over top of it. So if we have X, oh, I didn't say anything about that. Okay. How about, say that now. So if we have a map F from X to Y, you can pull back any bundle from X back Y back to X. Similarly, you can pull back difference bundles. So F star E V minus W should just be F star V minus F star W as elements in K of X for V minus W in KY. So in other words, we get a contravariant functor going from K of Y back to K of X. Okay, so we get an induced morphism. So in particular, if you have the base point or some base point including into X, and then mapping back to the base point, this gives us, yeah, how do we say this? This gives us a splitting of the thing. What's the most effective way to say this? just say it like this, that, I'll just start it on the board and write down what I was going to write down. Okay.
Do we need to know what a contravariant functor is?
It's something that goes like this. So like a continuous function from here to here will induce a morphism going the other way. Yeah. So it's a functor that reverses the order of the arrows, the direction of the arrow. So now I'll talk about reduced K theory.
Can I ask a quick question?
Yeah.
So for the rank function for a general X connected, this map is always surjective.
Yeah.
And the main abstraction would be kind of like the kernel of this map, whether like two stuff are isomorphic or not. So you're detected through. I guess my question is like, is there a? I guess there isn't, but is there like something useful about looking at the kernel of the rank?
It's given by this. So this inclusion, right, is going to give you a map going the other way in K theory, and we already know what this one is via the rank function. So if X is connected, then yeah, this is just, you can identify this morphism with the rank function. If that's not connected, this is just some other morphism. But over the connected component of X naught, you're picking out the things where the differences have the same rank. So this is the reduced K theory. And yeah, this is essentially what happens when you decide to ignore what's happening at this point and think about like non-point information over your space. So I'm going to say also note that the map, this restriction map has a splitting. You can go from K theory over a point, which is just given by vector spaces. So it's basically anything in here you can write as plus or minus the trivial bundle of rank n. And you just send it to also just plus or minus the trivial bundle of rank n. No, this is a vector space of rank n, and this is the trivial bundle of rank n. So this is actually a splitting for this map, which tells us that in fact our big K, once we've chosen a little x, our big K looks like a direct sum of the reduced K theory and the K theory of our base point. So for this reason, we tend to enjoy choosing a point and then only considering reduced K theory, just because it allows us to sort of discard a bit of information that we already know. Some theorems are only true for reduced stuff and not the unreduced stuff. Okay. So that's what I wanted to say about the growth deconstruction. So I'm going to move on to the second part of the first section. So let's say X is space, and then we're going to say that V, W bundles over X. And again, if X is not connected, I'm not going to require that they have the same, that they have constant rank over X. So you can have different ranks over different components. So let's say, how about we let this? And we say that V is stably isomorphic with two squiggles to W if there exists an N, so that V plus the trivial bundle of rank N is isomorphic to W plus the trivial bundle of rank N. So if we weren't talking about complex vector bundles and we were talking about real vector bundles instead, an example I could give is the tangent bundle of the sphere. So if you have the sphere Sn sitting inside Rn plus 1, and you have its tangent bundle, at every point you have its tangent space, you take then the normal bundle of the sphere, and you add those together, you get the tangent bundle of the ambient manifold. But the normal bundle is pointing outward at every point. This is actually a trivial one-dimensional bundle. So the tangent bundle of the sphere is stably isomorphic to the trivial n-dimensional bundle, if you're talking about real bundles. But if you're looking at the spheres that have a complex structure on them, it's actually not stably trivial as a complex vector bundle. Here you go. Chern class is obstructive, for example. But that's just some flavor. This is the definition I wanted to write down. And here's the theorem. If X is compact and Hausdorff, and I'm going to abbreviate this phrase as good, so I have to say it a million times, then you actually get an isomorphism. I didn't define it. Let's let kappa of X be complex vector bundles, but we identify the ones that are stably isomorphic. So the theorem is that this kappa group is actually naturally isomorphic to the K group that we defined formally with the Grothendieck construction. And the idea being roughly that, let's see, how do I say this? Oh, this isn't the theorem I wanted yet. Sorry. The theorem is just that this is a group. Yeah. Sorry about that. So if X is good, then this thing that we just came up with actually is a group. So what does this mean? This means if X is good, then every vector bundle over X has a stable inverse, essentially. There's some bundle that you can add to it to get the trivial bundle back. Oh, I've done something fishy, haven't I? Yeah, I don't like the way that I've done this. I'm gonna do it the way I initially did it in my notes and not try to ad-lib it. You can see there's 2 dimensions, so that you might be able to have to choose 2 different things. And then it's going to have a twiddle over it. Now that makes sense for a bundle with non-trivial rank to be stably equivalent to one which has a 0 rank. So this is a lot easier to believe is a group by just producing stable inverses. So good implies bundles have stable inverses. Pretty technical argument, but the idea is, I just wanted to give some idea because this is a really mysterious thing. Come up with, use goodness. This is the hard part. So we want to go from G from the total space V to some huge Rn. This is just the vector space Rn. You want it to be which a linear injected in each fiber. A linear injection in each fiber. So that's kind of the tricky part of the proof. Once you have something like that, you can fudge it into coming up with take your projection map cross G into X cross Rn. What that does is this embeds V into a trivial bundle. So once you've embedded your bundle into a trivial bundle, then it's possible to take like an orthogonal complement to get your actual stable inverse, because you're having them adding up together to some huge Rn. But yeah, like I said, I don't want to go into details of these kinds of arguments. There's lots and lots of books that you can go read about them in. And I would say that the source for this should should be Hatcher's vector bundles in K-theory. You can go read more about this approach. And the other approach, I'm basically just reading it out of my advisor's course notes on index theory. And I'll write down the source later when it makes more sense to do so. But this is coming from Hatcher. All right, now. Now there's a question of if we've actually done something new or not. If X is good, we have it. So if we choose a base point in X, then our set of stable isomorphism classes is actually isomorphic to our reduced K-theory. And what we do is we take a stable isomorphism class of some some stable isomorphism class of some bundle, and we send it to B minus the trivial bundle of rank n, where n specifically is the rank of the bundle over the base point. So this is why choosing a base point actually lets us come up with a difference here. To get this number n, we actually have to choose a base point so that we get a connected component, so that our rank actually has a number associated to it. Yeah. So for good spaces, we actually haven't done anything else new. We just get our old K-theory back. So what is the advantage of this stable isomorphism interpretation? Is that we did all this work in our bundle theory talks to come up with classifying spaces for bundles. And we, in fact, do get a classifying space for these stable isomorphism classes of bundles. So what do we get? So, how do I say this? Let's say, yeah. Let's say in the case X is connected. Bundles. So now we do have specific ranks because X is connected. So V is stably isomorphic to W if and only if, well, let's suppose one of them is bigger than the other. Let's say, for the sake of argument, n is at least as large as m. So we have our space X, and we have our classifying map for W into B, U, M. And we have our classifying map for V into B, U, N. And we have an well, not an inclusion. So we have an inclusion from UM to UN, which functoriality of our classifying space gives us a morphism to here. So these are stably isomorphic if and only if you can follow this classifying map all the way to some huge, huge, huge n, so that this function and this function become homotopic. So yeah, we call this CW, CV. Let's call this sigma for stabilize, and we're going from m to n. This is going to be n to n. So we want to say that if you do, yes. So if you classify W, and then you stabilize all the way into UN, that this should be homotopic as to classifying V, and then stabilizing all the way to the same spot. So stable isomorphism means that when you have this family of classifying space for complex vector bundles, it just means that if you have your two classifying maps, then eventually they become homotopic in this family of spaces. And so what you can do is is instead of choosing some arbitrarily large n, you can just take BU to be the co-limit of all of these n's. Right, you take the co-limit over all of these stabilization maps, and you get a space BU. This is also equal to B of the stable unitary group, which you can also just construct as a co-limit, or in this case it's even easier to just call it a union over all n, where you can choose your favorite way of identifying un inside the one, un plus 1. So, in fact, the reason I wrote this down is now that I get to say stable isomorphism classes of bundles is really the same. So kappa tilde is really the same as homotopy classes of maps from X into BU. So the stable isomorphism interpretation is good because this makes our functor like manifestly representable. We already know that this is a representable functor. And similarly, we can define kappa without the tilde. I'm just going to define it to be maps from X to Z cross BU. So these are things without ranks. If we wanted to add rank to everything, we can actually just artificially add it into our classifying space. So now a map from X into here is a choice of a stable isomorphism class of a bundle, and then an independent choice of some integer that represents its rank. And so, in fact, so maybe this is a bit surprising, maybe not by the way I've set up the narrative. So if X is good, the Grothendieck K group that we came up with is isomorphic to this stable isomorphism K group. So in fact, the ranks that were associated with this K group were pretty much like also an arbitrary choice. It just doesn't seem like it. Yes?
Sorry, I can't read what's going on with this, with co-limit BU. What is in the brackets there? BU?
Yeah, so write that more clearly, I guess. So the co-limit, so basically you have this family of classifying spaces. And for each n, you get a stabilizing map to the next one. And I guess it starts at BU0.
So that's n plus 1 there. Oh,
Yeah.
okay.
Yeah. So I don't even have to say, just say the co-limit of this diagram.
Yeah.
Okay, cool, thanks. Right.
These sigma maps are just like natural just embeddings of the spaces that we try the classifying spaces.
Yeah, these ones aren't embeddings, which is kind of confusing. So you have the embedding of the group into the next one, and then this is just going to be B of that embedding.
A B of the, okay.
So this is like iota mn, and sigma mn is B. This morphism. Yeah.
Can you repeat what the CW?
Oh, those are classifying maps. So we have actual vector bundles, complex vector bundles, and these are going to be classified by the classification theory by some continuous function into BUM. And
Is it easy to describe what that is, or it's just a
it's not easy to describe what that is. Like, it depends on the bundle. Like, do you remember, maybe you've left already, but I actually, using the Milner infinite join construction, I was able to like write down a classifying map given a partition of unity on your base space.
I can remember that.
So it's one of these things where it's valuable to know that there exists one.
Okay.
And to never try to actually write it down. Sometimes you can, but often it's just like there is a classifying map. Okay. So that's good. Just hit you with a bunch of confusing stuff. So now we get to do some tangible example. Right. Just wanted to establish representability. So let's look at the clutching construction. this is a general way of making bundles over spheres, any principal G bundle over a sphere. So take our usual decomposition of Sn into a pair of disks that meet at a hemisphere, one dimension smaller. This should be a D, of course. Meet at a hemisphere one dimension smaller. How do I say? Any G bundle can be trivialized over the disks because they're contractible. Trivialized. So the bundle is determined by this structure function of the intersection. And in this context, this gets the name the clutching function. And so this is going to be a G, I guess. I called my structure functions G. It's going to be on the intersection of these two trivialized charts, Sn minus 1, and it goes to the structure group G. Okay? So in essence, the outcome of this is that if you have principal G bundles over an n-dimensional sphere, then this is in bijective correspondence via this construction with homotopy classes of maps from Sn minus 1 to G. And I'm not taking pointed maps here. There's actually a difference when G is not simply connected. When G is simply connected, though, this is the same as the homotopy groups in G. But it's important to remember, because when you're dealing with real vector bundles that aren't necessarily oriented, then your G is not even a connected space anymore. Yeah, okay. So now I'm going to use this to do two very easy examples. So example 1. This is going to be a circle. Okay, so principal UN bundles over the circle by the clutching construction are given by homotopy classes of maps from the zero sphere into UN. So remember, this is just 2 points, plus or minus 1, and UN is connected. So this is trivial. So every complex vector bundle over the circle is actually trivial because the structure group turns out to be connected. So what this is going to tell us is that when we take vect, this is already a point. So the K theory, how do I want to say this? Which way am I going? Hold on, I'm confusing myself. It's not a point. Sorry. So this means that vector bundles are determined by their rank. That's what I meant to say. So just like when we had for the point, then K theory of the circle is going to be Z. And so in particular, if you go to reduce K theory of the circle, so if you discard that information of the point, then you're going to get 0. So the circle has no not interesting K theory. So let's go up one dimension and see if it's still true there. Okay. So now, principal UN bundles over S2. This is just going to be S1 into UN. And let's not. Okay. So this is a little more complicated. How do we approach this? Well, let's try with some small examples first. So for n equals 1, that U1 is the circle, or it's homeomorphic to, it's isomorphic as a group to the circle. And so, print U1 S2. So whether or not they're based, homotopy classes of maps from the circle to itself still gives you the integers. You can still compute a well-defined winding number. And they're determined up to homotopy by their winding numbers. Okay, so there are Z many rank 1 complex vector bundles over the circle. And if you remember, we also have, if you include UN into UN plus 1 and then take the quotient, you get a sphere of very large dimension. So for the long exact sequence in homotopy groups, it turns out that so UN to, in particular, this map is an ISO on pi 1. As long as n is at least 1. You're going to get a contractible space when n is 0. So what this means is that, in fact, all of these are Z, and they're not just accidentally all Z, they're all the same Z. There's some twistedness contained in U1 that any rank n complex vector bundle is essentially determined by this U1 twistedness. It's the same kind of twistedness even if you increase the rank. And so somehow all of the vector bundle information is contained in rank 1 bundles over S2. So we'll use the collection construction. Right, what can we do? Okay, so in order to get a bundle over S2, it suffices to give a map from S1 to S1. So we can do that. I'm going to call it H, even though my advisor's notes this notation is going to conflict. It's okay. So consider H bundle clutched by an identity S1. So what's happening, you have your two disks that you're gluing together along S1. You have trivializations on each of the disks. And the way that you glue the trivializations together is given by picking an element of U1 at every point in the circle. But the element that you pick is just that element of the circle. So if you rotate around the circle by a certain amount, your transformation is rotating by that much. So as you go around the circle, you're rotating the fiber exactly 1 time. So we'll call this H, and we're going to let blackboard bold B be the K-theory element H minus the trivial line bundle in the reduced K-theory of S2. So now, difficult result that I can't even begin to talk about is that this group is actually generated by B. It's a free abelian group on this element. So, like I was saying, how all of the bundle information over S2 seems to be contained in U1, just how do things twist over the equator, that's made like very seriously stated by this theorem. It says that even like when you go to K-theory, this twisting around the equator 1 time generates all bundles, all stable isomorphism classes of bundles. So this thing is what's going to get called the dot element. And it's going to manifest itself in a lot of different contexts in really weird ways. But this is our first appearance of it. So I should note also it's typical to take the bot element for the complex conjugate of this bundle And the reason that you do that is if you're really concerned about sign conventions. So we're not so concerned about sign. This is sort of the correct one to take. It makes signs and later formulas disappear. But since we're just doing it very informal, defining it without complex conjugation is just sort of one less conceptual layer for you to worry about. So I didn't want to have to really hammer out the signs. Okay, so that's some examples. And I'll go on to a different topic next. So this would be a good time for questions if anyone has any.
Just to make sure I understand, it's still it's reduced, like the key tilde is it's still Z. You're just marking what the generator is, but it's still Z. Or that's what the notation means in your theorem.
Yeah.
Just Z.
So this is like the free abelian group generated by this set.
Okay.
Yeah. I discovered this is a non-standard notation, I guess, but it seems to make sense to me. Okay. So that's one manifestation of the Bott element. So now, in order to get more serious, we need to start talking about relative K-theory. So this, I guess, is part of the Bott periodicity section already. So I've named it the Bott element. That's supposed to be kind of suggestive, because now we're talking about Bott periodicity. So we'll see in a bit, I hope, how those connect.
Can I have another question?
Yeah.
So this Bott element is is the image, if I recall like the map from the kappa, the state was like the kappa 1 to the K, this thing here should be the image of H under stable equivalence.
Yeah. Yeah, so it's like S2 is really CP1, and so you take the tautological line bundle.
I see, okay.
And this is, yeah, the H is the tautological line bundle.
Okay.
But you can also construct it like that.
Okay.
Or like that, yeah. Like that, yeah. So this is, it's interesting that you get the tautological line bundle by this kind of formal construction. But the H really is, yeah. Good remark. Okay, stuff gets crazy now. So let's let XA be a good pair. So what I mean by that specifically is that X is compact Hausdorff and A is a closed subset. So in particular, it's closed and also Hausdorff. So a K cycle on XA is a triple. So we have an E0, E1 bundles over X, and we have a phi from E0 to E1, bundle morphism. And so usually when we're talking about relative theories, we want to sort of think about, the A part we're trying to ignore. So the way that we're doing that is by requiring these to be isomorphisms over the subspace. This is a K cycle over XA. So this is sort of how we're trying to generalize going from vector bundles over X to vector bundles over the pair, where over A, they're sort of the same, right? So this is just saying we have a pair of bundles that are the same over A. So we'll denote it alpha, E0, E1. Actually, how do I like to do this? No. I'm already messing up my notation here. It's an E and an F. So we'll call it alpha. So alpha is, what is it, trivial? Acyclic. Phi is an iso. And we want to say that these two are related by a relation called concordance. So alpha 0 and alpha 1 are concordant. Concordant. If so, basically there's a case cycle on the product. On the cylinder that restricts to the case cycle on either ends. It's kind of like saying there's a homotopy. So alpha restricted to x across one of the endpoints is equal to alpha. Yeah. So it's not super important that you like totally digest that. I just basically wanting to tell you that there is an appropriate equivalence relation, and it is an equivalence relation. And then we're going to let con. These are case cycles modulo concordance, which I write tilde sub c. And we're going to let, what's the other word? Hackle. A. These are the acyclic case cycles. And then we define the relative K group, X, comma, A. To be the concordance classes modulo the acyclic ones. I think I've done something stupid. These are the concordance classes. Containing acyclic ones. So you mod out by concordance first because it's sort of the more natural way of considering two things to be equivalent. And then you say, okay, well, we want to ignore anything that's equivalent to an acyclic thing. Whatever you have left, this is your K theory. So a non-trivial element in this group is going to be like a pair of bundles and a morphism between them, so that there's no way of extending this isomorphism to an isomorphism between the two bundles. Bombarding you with terminology for now. And we also have pullbacks. So if F is a map of pairs, so if it goes from X to Y and sends A to B, we also get a pullback map on relative K theory. You expect, because you can just pull back the entire structure, pull back both bundles and pull back the morphism between them. And what else is on my list here? Yeah, we can add with direct sum, and then you can just block sum the morphisms together too. Okay, so bombarded you with terminology. Now the prank is my next result says that we already have this. We've already computed that. We didn't need to define anything new. This is actually something familiar. So let's go, XA is good. Well, I guess it doesn't have to be good for this clause, but let's take it for a base point. X naught. So if we go for the relative K theory, X relative to the base point, it turns out that this is actually just giving us our reduced K theory back. We already have this, it's just reduced K theory. So what if you have something that's not the base point? So you can take the quotient map. So you can take the quotient space X mod A and its natural base point, which is just A mod A. this induces an isomorphism on the relative groups. And so if you combine these two together, you get the corollary that, under the same assumptions, K of XA is nothing more than the reduced K theory of X mod A. So, you can ask, well, what was the point of doing all of that if we already have this? And the point is that actually writing down two vector bundles and a morphism between them that's an isomorphism on subspace can be a lot easier than actually writing down a vector bundle over a quotient space. Like, it's kind of hard to get your hands on these things, whereas here we have some really nice algebraic type of structure that we can work with on the level of these K cycles. And so I should now give you an example to show you that this isn't totally crazy. My notes are over here. Okay, page 11. That's not good. I have a feeling this is going to become a second talk where I also prove the Singer index theorem. Okay, so we're going to take, our pair is D2, the disk, and the circle, where we're imagining D2 being inside of the complex plane. Okay? And we're going to take, our bundles are going to be the same. They're just going to be the trivial bundle of the disk. And our map you're not going to believe it. We're going to take a complex number and a vector, even though these are just complex numbers. We can map it to the same point, but we're going to multiply this by the base point. Okay? So clearly if z is 0, this is not an isomorphism. But whenever z is not 0, this is an isomorphism. So this cycle, EF phi, this is giving us a relative cycle in D2 relative S1. And we just said this is the reduced K theory of D2 modulo its boundary. Well, hey, that's S2. And we're going to also call this thing the Bott element. So that Bott element and that Bott element are the same along this isomorphism. So this cycle that we created by doing this multiplication thing, you're going to see, it looks a lot like we're just doing this at the boundary, right? At each element of the boundary, S1, we're just multiplying the fibers that we want to glue together by this. But by considering K cycles, you don't have to do any gluing, you don't have to do any clutching. You just have to deal with these two bundles and one morphism between them, which is an isomorphism on this subset. So this is the way that K cycles become a little more workable than other things. Okay. So now I'm coming to a difficult point because there's about 5 minutes left and I have several pages. So I need to decide if I want to just skip a whole bunch of stuff or make the decision to talk again next week to give the rest of the talk. Does anyone have a preference? Should I just go again next week? I'm getting nods. Okay. In that case, I will finish up, I'll wrap up with the wrapping up function. Perfect. Here we go. So there's lots and lots and lots of ways of coming up with these K cycles using objects that arise naturally in a context like differential geometry. So this is probably the wrong word to use, but I'm going to use the word elliptic complex here. So we still have XA is good. XA good. Consider a sequence bundles over X. So we're going to have 0, D0, D0, D1, D1, and then D1, which is exact over A. So meaning that, i.e., the kernel of di restricted to A is equal to the image of di minus 1 restricted to A, but not necessarily exact over the rest. So if we choose a metric, and I'm not saying if, I'm saying let's do it, choose a metric so we can form adjoints. So we're going to have dk star is now going to go from ek plus 1 back to k. And what we're going to do now is go on this board, just so I don't go too low. Wrapping function, or wrapping procedure, or whatever. On this complex produces, a weird way of defining something, but here we go. So I'm going to call W E dot E dot. So our complex, and the W is the wrap. So what we're going to do is sum over all even k. Then we're going to map to summing over all odd k. So take all of the even terms and all of the odd terms, and the function between them is just d plus d star. So d plus d adjoint. So this is the wrapping procedure. Given an elliptic complex, we can just do this, and this is good because this ends up being a k-cycle. So in other words, when you do this, this actually becomes an isomorphism over A. You start with the sequence that is exact over A, and you do this funny d plus d star thing. It turns out to give you something which is an isomorphism over A. I'm not going to claim that that's obvious, but it is true. Yes, okay. So then I can just finish by giving 2 examples of doing this to stuff that looks really familiar. And then that's a perfect time to stop. Yeah, I didn't really have to go through this, but good. Okay, here's an example. So V is, sorry, X. State X is, no, I'll say it like this. V is a vector space which is isomorphic to C to the n. And then we're going to consider the following thing. So we're going to take V cross lambda 0 V. This is what I want to do yet. V cross lambda 1V. So these are the exterior algebras, the wedge algebras. 0. And so our dk is going to go from V cross lambda kV to V cross k plus 1 V. So we have a V here, and let's say a W here, plus, yeah, sure, another W. And what can you really do? Well, wedge the V onto the W. So this is exact over the non-zero vectors of V. And so the wrap of this complex in K of V relative to the non-zero vectors, I am going to give this the name Blackboard bold set V. This is the bot element of V. So if you started with C2, you can convince yourself that you get what we did. You get something equivalent to what we did over here. And now that I've set that up, there's something slightly more general you can do.
I have a question.
Yeah. Yes.
Don't.
I might be wrong.
But my question is about the d squared, because I would have v wedge w, but that's only 0 if n is you need it odd, right? Because you're going to be like -1 to the degree of x.
Don't we always have this? It's always 0.
But you have.
Because the field is a characteristic 0,
Okay.
right? Because
But
because normally, like, what you want to say is that this is minus this, right?
yeah, but okay, but in general, like it depends on. Maybe I'm being dumb. Let me think about it.
Yeah, I don't think
It's
it's
No,
There's just degree 1.
but like for any form, if you give me a general form, omega,
Yeah.
omega wedge omega is -1 to the degree of omega wedge omega.
There's a degree 1.
Oh, so I'm assuming that's degree 1. Okay.
Yeah, because they're just vectors.
Okay.
Yeah. Yeah, that's where it's important that it's coming from the base space. Yeah. No, that's a good question.
Wait.
Yeah.
But if I fix, like if I fix v equals like, if I fix a basis and I let v equals e1 plus e2, if I do v wedge v, I don't get 0.
Yeah, you should still, because it's a one form wedge to itself.
Oh yeah, actually I'm seeing v as a degree 1. Okay. Sorry.
Okay. It's okay. All good?
Yeah.
Okay. Slightly more general example. So in this case, we can consider all of these trivial bundles as just being the pullbacks of these bundles along the map from V to a point. We consider this to just be a vector's bundle over a point. So if you start with a genuine bundle, we can just do something really similar. Let's call it pi, and just do pi star of the exterior algebra. Pi star. Oh, let's say it's rank n. Yeah. Let's say there's a constant rank this time. And the differential is defined locally the same way.
Wait, sorry. I need to go back to this point.
Sure.
I feel I'm losing my mind. Can you do v equals e1 plus e2 and just compute v wedge v?
Yeah. Don't make your ones look like wedges. Stop it.
I know that e1, that's 0.
Yeah, so these are
Oh,
0
yeah, sorry,
because
I'm
of the
done.
one
Okay.
forms, and then
Again, minus
this,
e1. Yeah. Okay. Yeah, sorry, I'm very dumb.
It's late in the day. With D defined locally, or like fiber-wise, in the same way. So if you're at a point in V, so in particular, you're going to be, so if you're at a point in this vector bundle, you know what it means to wedge with that vector, because it's a vector in a fiber. You can do the differential in the same way, same formula, and this is again, so analogously, this is exact over the total space minus the 0 section. This is the 0 section. So this gives us then a element in k of v relative to v minus the 0 section. I'll just write it like that. And this gets the name tau sub v. This is the Tom class of v. So if you've ever seen Tom classes before, this is surprising that it takes this form, but this is actually, if you actually go and you actually do all of the details, this gives you a proof that complex vector bundles are orientable in complex K-theory. And it's interesting that these bot elements are actually just Tom classes of bundles over a point. So this is teaser for next time, I guess. We're not going to be doing too much more like this, but I just wanted to show that like you can very readily come up with relative classes using this wrapping up procedure, as long as you're able to actually construct an exact, like a sequence of bundles that's exact over some interesting subspace of your space X, but not exact over all of X. So in index theory, your elliptic operators have something called a symbol class that gives you one of these complexes. And we're going to see that this is the way that you relate your analytical index. So out of your Fredholm operator, blah, blah, you actually get a K-theory element. And that's that K-theory element. You have to follow along the sequence of arrows, finally gets you to an integer that's called the topological index. And the theorem is that this is the same integer as the analytic index of your Fredholm operator. Okay, so that wasn't as far as I wanted to get, but I'm done for now. I've had my time.
I have a question.
Yes.
In order to get the cohomology class from here, you would just take some sort of Poincare dual.
Cohomology?
Yeah, because like in some class you can also define it using a cohomology class, right?
Yeah. You
So-
take the. That's a really good question. Okay, so you get a Tom isomorphism going from k of x to k of this relative thing. So this is the Tom isomorphism. This is going to be given by just product with the Tom class. And you can do something similar in cohomology. You define a Tom class, and you get also a Tom isomorphism. And I'm going to call this cup with T sub v. And, okay, going from K-theory to cohomology, the most natural thing to do, literally, haha, is take the Chern character. So you can go from the Chern character from K-theory to cohomology. And you can do the Chern character here as well. And the problem is that this doesn't commute. There's an issue that this doesn't commute. And the failure to commute is actually like a characteristic class. It ends up being a natural transformation from K-theory to, or from bundles to cohomology, and it gets called the Todd class. So there's a formula relating the K-theory Tom class and the cohomology theory Tom class that goes via Chern characters and Todd genus, Todd class. Yeah,
That's insane.
so that's part of, so when you look at the cohomology formula for the index class, that's why we have this Todd thing showing up.
I see.
It's by like chasing this diagram around.
That's insane. Okay. I did not expect that answer.
Yeah, good question. Are there more questions? I think that was a very high-level, confusing talk. So. Oh, no, yeah, I have to give the source. This is, yeah. So most of this content I've been getting out of my advisor's notes. It's called, I think it's called A Lecture Course on Index Theory. The guy's name is Johannes Ebert. If you're just looking him up, you have to do like Johannes Ebert math, because I guess there's like a famous soccer player with this name as well. Yeah, so that's the source that I've been using for most of this stuff, except for the stuff that I said was from Hatcher. That was the stable bundle interpretation. Yeah.
Are there other interesting type of maps you could get? Like that are not just locally, like just wedging?
Yeah, you just take the Durham complex.
Okay, that's what I
With
was curious
D?
about.
Yeah, you take the Durham complex just with the normal differential, and then the index class you get from that. When you go all the way to cohomology, you get the Euler class. Yeah. There's another one you can do with like the Hodge-Star operator that ends up giving you the signature.
I see.
Yeah.
Is there?
Which is, I guess, Poincaré duality is what's going on there.
Okay.
Which is really weird.
Do you remember what's the relation like for rank 2 bundles? I think it was. I'm crazy. Wait, is the Euler class related to? Is the Euler class is related to the Tom class, isn't it? It's like the pullback.
Yeah.
It's not, I'm trying to piece the piece together between this, but then you tell me the Euler class also shows up. So I'm curious, like, what's the piecing?
Let's see
in all of these?
here. So if we have the total space relative to this, so this is where the Tom class lives, the cohomology Tom class. And then you have the zero section itself, x relative to the empty set, maps to v, comma, v minus this. So this is, you can interpret the zero section as a map of pairs. And so this goes the other way downstairs. And so the Tom class does go to the Euler class.
Yeah.
Yeah, you're just pulling it down by the zero section.
Okay. But now you're telling me that if I do this wrapping, wrapping
Yeah.
procedure with the Durham complex, I would end up getting. Well, what did you say about getting the Euler class if I use the Durham complex?
Yeah, I mean, like you wrap it up and then you get your K-theory class.
Yeah.
And then you apply the cohomological formula for
Okay.
the index, and then when you work all of that out, you end up getting the Euler class
Okay.
comes out of that.
I
So
see.
it's not like a direct thing.
Okay, I see.
Yeah.
That answers the question. Okay.
Yeah, yeah. The meat, like the important part is that when you actually compute the topological index, you get the Euler characteristic.
I see.
But at even like a higher level, you're actually recovering the Euler class. And so like the signature one, that's like an exercise. That's like go and compute Hirzebruch's L classes by like writing down the representation for this Hodge-Star complex and like doing the characteristic class calculation. You can do it. You can like derive the L classes just from the index formula.
I see.
Yeah, my advisor made me do that. It works. It really does.
That's cool.
Evan, do you have any questions?
Are you going to show the notes?
It's fair. Am I going to show the notes?
Yeah, do you think you could add these notes you covered today? Because I got lost in some parts, so I would like to like review them for the next one.
Like, yeah, I could just like scan them or something.
Yeah, just take a picture.
Yeah, I can do that. Try to remember to do that. Might have to remind me because bad at stuff like that.